we're going to be looking at here solving what's called systems of linear equations. So throughout the unit, we'll look at different ways of doing that. Here we just want to talk about what is a system, what does a solution mean, and then we'll start looking at how can we solve a system graphically, so using a graph, okay? So a system of linear equations consists of two or more linear equations in the same variable. So the examples we can see up here, we'll notice both the ones on the left are both in slope-intercept form. So they both have the same variables, a y and an x, okay? The ones on the right, might look a little different. They're not in slope-intercept form, but they're still two linear equations with the same variables in them, right? So we put them together, we call that a system. A solution to a linear system is simply an ordered pair that is a solution to both things, okay? So the example you see on the screen there, I've got 2x minus y equals -3, y equals x plus 2. The ordered pair 1 or -1 comma 1, we can see right there, right, is a solution to both of those. You can see the work over here, right? 2 times -1 minus 1 is -3. So if I put in the x and the y value, right, I get a true statement. Okay, y equals x plus 2. Well, if my y value is 1, my x value is -1. 1 is equal to -1 plus 2. All right, so a solution to a linear system is simply, in this case, it's going to be a point that is a solution to both, right? An x value of -1 and a y value of +1 is a solution to both of those equations. So when we're trying to find a solution, we're looking for that point or those points, and we'll look at later on if you can have more than one point. But that point that is a solution to both of those things, okay? And again, we're talking linear, which means they're going to be a straight line. So if we think about, straight lines on a graph, it's where they cross, okay? So a consistent independent system is a linear system that has exactly one solution, okay? Lines are distinct, meaning they're different lines or independent, and they intersect, okay? That's where that word consistent comes from. So you can see on the graph, right, you've got that red line and that blue line there, right? They intersect at one point, okay? So that's going to be their solution, right? That point is a solution to the red line because it's on the red line. It's a solution to the blue line because it's also on the blue. So again, when we're talking about solution to a linear system, if it's a consistent independent system like that, you're going to have one solution. It's that intersection point. Okay, so you can see the point of intersection there would be at 2, 3. We'd say that's the solution to that system. All right. So we're going to look at how can we solve linear systems different ways. Like I said, we're going to start with by looking at how we can solve it using graphs. Okay, because if we can find that point of intersection on the graph, we can find that solution. All right. So our steps we're going to go through. We're going to graph each equation in the same coordinate plane. Right. Again, we have to look at where they intersect. So they need to be on the same coordinate plane. And again, most of the time it's going to be easier to write it in slope-intercept form first. If you can find the x-y intercept, sometimes that helps too, but most of the time we're probably going to make sure they're in slope-intercept form. Look at where they intersect, and sometimes you might have to estimate a little bit because if you're not drawing your lines exactly straight or in the exact right point, it might be a hair off. So we're going to estimate the coordinates of the point of intersection and then check the coordinates algebraically by substituting into each equation of the original system. So we're just going to verify that our estimate is actually the solution. Okay. All right. So if I look at solving these, make sure I'm on the right page here. Here we go. We're going to solve the linear system by graphing. All right, so y equals 4x minus 5 and y equals -2x plus 1. Both of those are already in slope-intercept form, so we're simply going to graph those. Okay, y equals 4x minus 5, so my y-intercept is at -5. And I'm going to use my slope to find another point. So my slope is 4 over 1, so up 4 and over 1. Okay. And sometimes when you want to try and get it accurate, maybe do an extra point here. Okay. And then I'm going to use a straight edge because, again, we want to be accurate with our intersection points. So we're going to try and get these as close to accurate as we can. All right, so straight edge helps us with that. Okay, so there's my first one. Change colors here and do my second one. Okay, so y equals -2x plus 1, so your y-intercept is at +1, and our slope is -2, so I'm going to go down 2 and right 1. Down 2 and right 1. Now what you might notice already is that I put a dot right where that other dot was. Okay, get my ruler out. So we kind of know already where that intersection point is going to be, but let's draw the graph just to check it here. Here we go. Okay, so it appears that the intersection point is right there. It's at 1, -1. Okay, let's double check that and make sure that's accurate. So I'm thinking it's at 1, -1. All right, if I try that, so plug those in. So y equals 4x minus 5, so -1 equals 4 times 1 minus 5. Well, 4 times 1 is 4. 4 minus 5 is -1, so I know it works there. Okay, -1 equals -2 times 1 plus 1. Well, -2 times 1 is -2. -2 plus 1 is -1. Those are equal, so I know that checks out, right? So that's going to be my solution. It's going to be my solution. Okay, all right, let's do another one. Y equals -2x plus 3, so 3 is there. -2, so down 2 and right 1. Again, I'll do a couple just to make it a little more accurate. Okay, I'm going to try and freehand this just to kind of show you. Sometimes you can get away with it. But again, if it looks close, like we'll have to do a little estimating here. Y equals x minus 6, so -6. Okay, and then my slope is +1, so up 1 over 1, up 1 over 1, up 1 over 1. Okay, so it appears that there's my solution. So that's at 3, -3. And let's double check that and make sure that works. So y equals -2x plus 3. So -3 is equal to -2 times my x value. So -2 times 3 is -6. -6 plus 3 is -3. So -3 equals -3. So it works for that one. Okay, so I know that works. Let's try my second one. I'm pretty confident this is going to work, but let's always verify here. -3 is your y value. X is 3 minus 6. Well, 3 minus 6 is -3. Those two things are equal, so we know that's our solution. Okay, we know that's our solution. All right. Okay. Now, if we move to these second ones, one thing we'll notice here is we have one in slope-intercept form. Our second one isn't. Okay. So we'll look at a couple ways of doing this. All right. The suggestion was write it in slope-intercept form. And you're certainly welcome to do that. I'll kind of show you another way we can do it here with this, but let's graph the first one first. Y equals -2x minus 3. Okay, so there's my y-intercept. My slope is -2. So down 2 and right 1. Let's go up 2 and left 1. Oops, there we go. And let's just get a little more accurate again. Makes it a little bit easier to draw that line. Plus you get more dots and there's more chances of intersecting. So now the second one here, I got a couple of options. I could rewrite that in slope-intercept form. Okay, so I could bring my x over. Okay, like that with subtraction. Then I divide everything by -2. So I'd have y equals negative and a negative make positive, so 1/2 x minus 3. I can certainly do that. Okay. The other way is, if you remember back to intercepts, right? If I basically make my y value 0, x would be 6. Okay, so that would be my x-intercept. All right, and then if I make my x value 0, okay, well, -2 times -3 is +6, so that's my y-intercept. Okay, so that's another way you could do it. I could also use slope-intercept form, okay, and go from there, up 1 over 2, up 1 over 2. You can see we're going to get the same line there. So you always have options. Again, I think intercepts are quick ways to do it if the equation sets up nicely for it. So, but again, you're certainly can rewrite that in slope-intercept form. All right, so there is my point of intersection. It appears to be on the y-axis, 0, -3. And again, I know that it's a solution there. I've checked it in this one already with the intercepts, and I know it's my y-intercept. So I don't necessarily on this have to like formally check it because I know there's solutions to both with that. But again, if you're not sure, plug them in, see if it works. Okay, but I know this is going to be my solution. Right. Again, next one. Again, this one to me sets up nicely to do intercepts. Right. If I make my x value 0, I have y equals -7. So that's my y-intercept. And if I make my y value 0, okay, I would have -x equals -7. Well, or we could read that as the opposite of x equals -7, so that would be +7. So that's my x-intercept. Again, I could rewrite that as y equals x minus 7 and use that as my slope and y-intercept as well. So depending on what you're comfortable with, what's easiest for you, that would be our graph. Okay. Our second one there, x plus 4y equals -8. All right. So again, my x-intercept, if I make y value 0, my x-intercept would be at -8. If I made my x or my y value 0, I'm sorry, my x value 0, 4 times -2 is -8. So my y would be at -2. Okay. Or I could rewrite it in slope-intercept form, in which case I'd have y equals -1/4 x minus 2. Right. So if I need to, I could go down 1, 1, 2, 3, right 4 from there. That is a bad line, which is why we always want to double check our point. But it looks like it intersects there at 4, -3. Okay, let me erase a little bit of this here. So 4, -3. Let's just verify that. So the opposite of x plus y. So the opposite of 4 is -4 plus -3 is -7. So that checks out. 4 plus 4 times -3, well, 4 times -3 is -12. 4 plus -12 is -8, so that also checks out. So that's our solution. Okay, that's our solution. All right, so again, we want to graph both lines. Okay, find that point of intersection, and then just verify that that point of intersection is actually the solution. Okay. Let's look at just a couple more examples here. Right, -x plus 2y equals 3. Now this one doesn't really set up as nicely to do intercepts because 2 times like 1.5 is 3, and graphing 1.5 sometimes is tough. So let's rewrite this one into slope-intercept form. So if I move my x over, I'd have 2y equals x plus 3, and then divide everything by 2. So I'd end up with y equals 1/2 x plus 3/2, or 1.5. Right. So again, we still kind of have to estimate there. All right. So my y-intercept is at 1.5. Okay. My slope is 1/2. So I'm going to count up 1. Oops, I messed that up. This is why sometimes when you get halves, they're difficult. So 1.5, we move to 2.5. So up 1, right 2, up 1, right 2, and so on. And I'm going to use my ruler on this just to kind of make sure I'm getting it as accurate as possible, since we're kind of in between points here. Okay. And then my second one, get a different color. 2x plus y equals 4. So again, if I move my 2x over to the other side with subtraction, I'd have y equals -2x plus 4. Okay. Or I could do my x and y intercept. 2 times 2 is 4. Either way works. Okay. So 4 is my y-intercept. I'd count down 2, 1, 2, right 1. Right there, down 2, right 1. So it appears, holy cow, that is a bad line. Okay. Some people are really good at drawing straight lines. I'm going to use my ruler. There we go. So it looks like there's our point of intersection, 1, 2. Now I'm not 100% confident in this, just because, again, that first graph is a little bit tougher. Getting exactly a half sometimes is hard. So let's verify it. Let me get rid of some of this so I have some space here. Let's verify it. Right, so 1, 2, so x is 1, so -1 plus 2 times 2 equals 3. Well, -1 plus 4, that's equal to 3, so I know it checks out. Okay. And then let's try the second one. So 2 times 1 plus 2 should be equal to 4. Well, 2 times 1 is 2, plus 2 is 4, so that also checks out, right? So this is going to be my solution. That's my solution right there. All right. Next one, x minus y equals 5. Okay, I'm going to use my intercept, so I know 5, right? Again, I basically get rid of the y. Well, x would have to be 5 in that case. And then we get rid of the x. Getting rid of really means we're turning it into 0, but this is kind of the shortcut way of doing it. I like to just kind of cover it with my finger, but since I'm on the screen here, scribble it out. So the opposite of y is 5. Well, y would have to be -5. The opposite of -5 is 5. So my y-intercept is -5. Okay. Again, you could rewrite that in a slope-intercept form and get y equals x minus 5 if you wanted, but sometimes intercepts are a little bit quicker. Okay. Missed my dot there a little bit. We'll see if that affects it, but we're going to keep going. 3x plus y equals 3. Again, intercept set up nicely, right? If I get rid of my y value, 3 times 1 is 3. So my x-intercept's at 1. Okay. If I scribble out my x value, I have y is equal to 3. Like so. Okay. It looks like our slope is down 3 and right 1, so I'm going to do that again. 1, 2, 3, right 1. Okay. Holy cow, that's way off. Again, straight edges are good things to use on this, but I want to demonstrate without a straight edge what kind of happens, right? So it looks like it's hitting right there, but our line got a little off. So I'm always going to try a 1 first because I have no clue if that halfway in between, is that 3/4 of the way. So let's try and estimate. It looks like it's probably going to intersect there if my line was exactly straight. Okay, so that looks like 2, -3. So let's just verify that. So 2 minus -3. Right, we change that to plus positive would be equal to 5. So it checks out there, so it's looking good. Okay, and then why it's doing that. There we go. And then 3 times 2 plus -3 is equal to 3. Well, 3 times 2 is 6. 6 and -3 make 3. So it checks out. Okay, so right, if you kind of do what I did there and you're kind of sloppy with your lines, again, that's why we always want to kind of verify, right? Kind of check and see, well, it looks like that, plug it in. Okay, if it happens to not come out, you might have to erase your lines, see if you did them correctly, draw them a little straighter. All right, with that, but that's what that should look like. So again, we're looking for that point of intersection. Okay, now there's some special situations. So a system of two linear equations can have one solution, right? We've seen a whole bunch of examples of that, right? One point of intersection. Can have no solution, all right? Or infinite number of solutions. So let's think of what that means, right? So one solution means, like we just saw in our all of our examples we just did, right? So one solution means two straight lines that intersect only once, right? Okay. No solution. Well, that means the lines can't touch, right? So what does it mean if two lines aren't touching each other, right? We learned this last unit. That means they're parallel. Okay, and if we're looking at an equation, how do we know if something's parallel? Remember, parallel means they have the same slope, right? So let's say I had an equation y equals 1/2 x minus 2, y equals 1/2 x plus 4, right? They've got different y-intercepts, but those two lines are going to be parallel to each other because their slope, right, is the same. So those would not have a solution. They're not going to touch each other, right? There's no point where they're going to intersect, right? Another way to think about it mathematically, I can't take half of something and subtract 2. Take the same number, take half of it and add 4, and ever get it to be the same, right? They're always going to be different. All right. And then an infinite number of solutions. So that means they intersect each other infinitely. All right. Let me get a graph here. Free. So, right. Think about that. To be infinite, it's being dumb on me. Let me try this again. Okay. Let's say I had a line. Well, to have infinite solutions, that means they basically have to be the same line. Okay. So an infinite number of solutions means the lines are the same. Okay, so sometimes equations might be disguised to kind of look different, but when you rewrite them in slope-intercept form, the exact same. Right? Let's say I had one that was y equals 2x plus 3. Okay. All right. Well, let's say then my second one was y minus 2x equals 3. Right. So they look a little bit different, but if I were to take my last one here and take the 2x and move it to the right, right, with addition, I'd end up being the exact same. So an infinite number of solutions just means it's the exact same equation. Lines are the same equation, right? Sometimes you'll see equations that are in different forms and they look different, but when you rewrite them into slope-intercept form, they're the exact same. All right. So again, if we want to give some examples here, a linear system with one solution, right? You're just looking for something with different slopes. Okay. Y equals 2x minus 1. Y equals 1/3 x plus 2, right? The slopes are different, so we know they're going to intersect. Okay. Linear system with no solution, again, that's going to be parallel lines. So y equals 1/4 x minus 1. Y equals 1/4 x plus 2, right? Exact same slope. Exact same slope. They're not going to touch each other. Okay, and a linear system with an infinite number of solutions, again, you're just looking for two that are the same. 2y plus 4x equals 3. If I double all those, I'd have 4y plus 8x equals 6, right? Those are going to be the same. Just, again, if I divided all those by 2, it'd be the exact same thing. So, again, one solution, different slopes, right? They're going to intersect once. No solution, the exact same line, meaning their slope is the same. I'm sorry, let me back up. No solution means not the exact same line, means parallel lines, my bad. Parallel lines, which means their slope is the same, but they have a different y-intercept, right? Because they're touching the y-axis at different points. And infinite number of solutions are the exact same equation, right? And you've got to be able to solve these into a slope-intercept form to tell that, right? So this would be like y equals negative 2x plus 3/2. This one would be y equals negative 2x also plus 3/2, right? It's the exact same. All right. Again, solving linear systems graphically using a graph, you're either going to have one solution, they intersect once, they don't intersect, they're parallel, or they're the exact same line and they have an infinite number of solutions. Okay.